Children, today we are going to begin with the colligative property, osmotic pressure. Though I have given you introduction of osmotic pressure in the last video. Before that, let's have a revision again. What is osmosis? So again, you just pay attention here. This is the diagram given. Osmosis is a spontaneous process and involves the flow of solvent from a dilute solution or solvent to a more concentrated solution when the two are separated by semi-permeable membrane. Here it is a semi-permeable membrane and the solvent molecules are passing from here to there. This you have learned in the last video, you have already learned, but I would like to show it again that how it happens. The solvent molecules are passing from here to there. Is that clear? Now if an external pressure is applied on the solution side, let's see what happens. You can see a piston here and it is a movable piston. So if this external pressure is applied on the solution side, that is a more concentrated side, let's see what happens here. It is equal to the osmotic, it develops a osmotic pressure here. Now what is osmotic pressure? It is equal to the external pressure which should be applied on the solution side to prevent the flow of solvent into solution through semi-permeable membrane. So what is osmotic pressure? It is simply the external pressure applied on the solution side to stop osmosis here, that is at the semi-permeable membrane. Simply a little amount of the external pressure applied. So what happens? This osmosis stops here at semi-permeable membrane. Now let's see one more very relevant term here. This is reverse osmosis. So, when the osmosis, which is a natural process, is reversed by applying a pressure greater than the osmotic pressure on the more concentrated solution side, it is called reverse osmosis. I hope you understand. What does it mean? If the external pressure is that much only which can stop the osmosis here, then it is said to be osmotic pressure. If this external pressure a little more means what? That this external pressure applied here can reverse the process. Reverse the process of osmosis means what? That is known as the reverse osmosis. And what happens actually in this process? That the solvent particle start moving from the solution side to solvent side. This technique is used in desalination of seawater. It is a very important technique which is used in our everyday life. Actually, what happens? The seawater contains lots of dissolved salts which make it hard water. When seawater is kept in contact of fresh water through a semi-permeable membrane and pressure higher than osmotic pressure applied from seawater side, reverse osmosis takes place. That is what? Water which is a solvent here will be forced to flow from seawater side to the freshwater side, leaving behind dissolved salts, and in this manner the seawater is converted into soft water. This you can imagine. Just imagine the seawater is at this side and fresh water is at this side, and when the reverse osmosis is applied here, the solvent, which is the water here having lots of dissolved salts, this solvent particle will be forced to move from the solution side to solvent side, and obviously it is going to be tapped out here and considered as soft water. So now what you have learned? You have learned osmosis, reverse osmosis and osmotic pressure. Now let's begin with this laws of osmotic pressure and Vant Hoff equation. Reason is that because this is the implementation of these laws here to find out the molecular mass of the non-volatile solute using what? Osmotic pressure and Vant Hoff equation. So let's begin with that. Vant Hoff in 1877 established that solute particles present in a solution behave exactly like the molecules of a gas, and the osmotic pressure of dilute solution is equal to the pressure which the solute would exert if it were a gas at same temperature and occupying the same volume as that of solution. So what does it mean actually? Very dilute solutions, they behave like gases in similar condition. Van 't Hoff also established that ordinary laws obeyed by gases are also obeyed by dilute solutions. Hence, ordinary gas laws, when applied to solutions, they are referred as laws of osmotic pressure. Now, we are going to begin with this. Let's see here. Let pi be the osmotic pressure and see the concentration of a dilute solution. Now, according to Boyle's Vant Hoffs law, this pi is directly proportional to C. And what is this C? Let's see. This particular C is molarity or concentration. It's given here. C is equal to N by V. What is N? N is the number of moles in definite volume of a solution. The unit is what? Moles per liter. If we consider N as 1, means what? Number of moles are 1. So what I can write here, or you can write it immediately, that C is going to be 1 by V. And what is that? It is and 1 by V, if I put here, that is pi is directly proportional to 1 by V. This is what? This becomes Boyle's Vant Hoffs law. Clear? Now the second equation, let's see. This osmotic pressure pi is directly proportional to T at constant concentration. And this is what? This is Charles Vant Hoffs law. Now on summation of these two, you can see I can write here pi is directly proportional to C and T. Now since this is directly proportional, one proportionality constant is used here, which is R. This R is known as solution constant. Its value is same as gas constant. And the value, I hope you remember. You should remember. It should be on your fingertips. It is given here 0.0821 liter atmosphere per Kelvin per mole. Now we come back. Come back on this particular equation. This is pi is equal to CRT. Let's make it more simple. I am putting the value of C, that is what, N by V here instead of C. So it becomes pi is equal to N by V RT. You know what is T? T is the absolute temperature. W, now let's see further. Now what is N? N is number of moles. We can write it W upon M. What is this W here? W is the weight of solute upon molecular mass of the solute, which is a non-volatile solute here in this case. Now I am putting the value of N here in this equation. The value of N is being kept here like this. This becomes pi is equal to W by M RT V. Now let's see what is what. W is the weight of solute in grams. R is solution constant, already mentioned here. T is absolute temperature in Kelvin. M is what? M is the molecular mass. Pi is the osmotic pressure in atmospheric pressure. Then V is the volume of solution in liters. Now let's see. We can transform this particular formula in this way. That is the formula used here. Let's see. If moles of solute given, then we use this formula. Pi V is equal to nRT. Moles of solute, N. If mass of the solute given in numerical, we have to use this formula. That is pi V equals W by M RT. Mass of the solute. Molecular mass, we should know. Mass of the solute given. So we can find out either pi or V or any other thing if we knows rest of the values, numeral values of the rest of the factors here. If molar concentration of the solute is given, that is what C is given. Molar concentration. see, this is N by V. N by V molar concentration is given. We have to use this formula. Now there is one more transformation of this formula, but before that you have to know what is this term. There are three more terms given here: isotonic, hypertonic and hypotonic. Now let's see what is isotonic. Isotonic solutions are those having same osmotic pressure at a constant temperature. When two isotonic solutions are separated by semi-permeable membrane, no osmosis takes place. So if in a numerical it is given that two solutions which are isotonic, what formula you will use here? What is the implementation here? See, when two isotonic solutions, their concentrations are same, so I can write C1 equals C2. On opening, what is there? This C is equal to N by V. So C1 is equal to N by V. N1 by V1 equals N2 by V2. Now again if I open, N is what? Number of moles, which is equal to W by M. See here, this is W by M. So I can write here W1 upon M1 V1 equals W2 upon M2 V2. This is one more transformation of this formula here, this particular formula, right? Now let's see something more. What is the inference drawn here? Let's see. Osmotic pressure pi depend on molar concentration, which is C, of the solution and temperature T. It does not depend on nature, composition and structure of solute. Hence, it is what? It is a colligative property. And what have you learned about colligative properties? That these are the properties which depend on the number of particles and does not depend on their nature. And what is this molar concentration? Molar concentration is actually number of particle, which is molarity, number of particle N by V. Fine children. So before winding up this video, let's have one numerical. See, I have done it here. Very simple. Formula oriented numerical is there. See, 10 grams of an organic substance when dissolved in 2 liters of aqueous solution gave an osmotic pressure of 0.6 atmosphere at 27 degrees Celsius, where R value is given. It is the same 0.0821 liter atmosphere per Kelvin per mole. Now what you have to find out? What is molar mass of organic compound? Right? This we have to find. Now see again into the numerical. Write down what is given. Weight of solute is given 10 grams. Volume is given 2 liters. Osmotic pressure given 0.6 atmosphere. Temperature given 27 degrees Celsius. We have to convert it in Kelvin. And you can see here, by implementing the numeral values in the formula is same. See the asterisk here and the asterisk here. This formula I am using here, and I have put the values given in the numerical, numeral values in the formula, and I am getting this answer. The molecular mass of the non-volatile solute is this much, 205.25 is the answer. Now that's over. Now next is Vant Hoff factor, which we will be discussing in the next video.